This is the review from Friday. So with this one, you just work out the problems. We're only going to do the half-life problems together, and then I'll post the answers. Oh, this looks weird on my end. It's fine. I'll post the answers after. So number one, it says, what is the half-life of a radioisotope if 25 grams of the original 200 gram sample of the isotope remains unchanged after 11.46 days? Okay, so they want to know what the half-life is. So we don't have that information. Our initial, I'm just going to put I because I don't feel like writing it all out, is 200. Okay, so I like doing the chart. So I'm going to do at 0, at no half-life, you're starting at 200 grams. And they want to know what's the half-life hold on. What is the half-life of a radioisotope? Okay. So we're at 200 grams. 1 gram, or 1 half-life, will take you to 100. 2 half-lives will take you to 50. We're going to do 3, takes you to 25 grams. Okay, so this is where they want to stop. So it's saying after 3 half-lives, 11.4. After 3 half-lives, you end up with 25 grams. Don't worry about this line. I just wanted to clear some space. Okay, so it took 11.46 days for all of this to happen. Okay, so this all happened in 11.46 days. So what you would do is you would divide 11.46 divided by 3, and that is going to tell you how much 1 half-life was. So I'm just going to plug that into my calculator. 11.46 divided by 3. So each half-life is 3.82 days. Okay. So 2 is just asking about the particles that has the greatest mass. So that is talking about like alpha, beta, gamma, positron, which one has the highest mass. And it's actually going to be alpha. Number 3, an original sample of the radioisotope fluorine, that's a typo, 21, has a mass of 80 grams. Only 20 grams of its original sample remains unchanged after 8.32 seconds. What is the half-life of fluorine 21? So this is going to be the same one as number 1. So you start, they want to know what the half-life is. Your initial is going to be 80. So no half-life, you're starting at 80 milligrams. 1 half-life, you're at 40. 2 half-life, you're at 20, which is where you're stopping. All of this happened in 8.32 seconds. So you're going to do 8.32 seconds divided by the number of half-lives that happened. So 2. And that'll give you 8.32 divided by 2. 4.16 seconds for 1 half-life. So describe the 4 types of decay. So you're going to tell me what alpha is, beta, gamma, positron. And this is all from your notes from last week. Okay, an original sample of K40, that's potassium, has a mass of 25 grams. After 3.9 times 10 to the 9, this is supposed to say seconds. Grams of the original sample remains unchanged. What is the half-life of potassium 40? So number 5 is identical to 1 and 3. So that one, you can work it out. Also, I left my scientific calculator, and I cannot plug this big old number into my phone. List the nuclear emissions in order from least penetrating power to the greatest. So if you go in your notes where we talked about, I think the notes are titled Nuclear Chemistry, there is a chart that shows you which one has the most penetrating power. And in notes, it's like a picture, and it's like the rays going through like different products. So make sure you look at that. The stability of an isotope, it's based on its neutron to proton ratio. What is the mass number of alpha particle? So alpha is 4 to alpha, or it's a helium atom that has the same numbers. So hopefully you remember your mass number of an alpha particle is 4. Number 9, list the nuclear emissions in order of increasing charge. So increasing charge means it's going to be smallest to greatest. So it's going to be beta, gamma, so hold on, this is beta. So beta is -1, positron is +1, and then alpha is going to be 2. This one I can't see right now, but basically which one is going to show you positron decay? Positron is going to be plus, it's going to be E plus, and there is a type, sorry, there is a typo, so don't worry about this one. Okay. What is the new, don't mind that, but I don't feel like recording this again. So what is the neutron ratio of cobalt-58? So let's look up cobalt in our periodic table. Hold on. Okay, so cobalt is going to have an atomic number of 27. So you're going to do 58 minus 27, and that's going to give you 1. This is 3. So it's going to be 31/27. This one is just asking for the ratio. You do not need to tell me if it's stable or unstable. Base your answer on the following question on the given nuclear equation. What element or what particle is represented by X? I can't, like, you can see how weird mine looks, so I'll post the answers of this. We won't do this one either. Alpha particles and beta particles differ in mass only, charge only, both mass and charge, neither mass or charge. It's going to be both mass and charge. Alpha has a charge of 2 and a mass of 4. Beta is going to have 0 and -1. Which statement best describes gamma radiation? Gamma is going to have a mass of 0 and a charge of 0. So this one is going to release a photon, which we'll talk about later. But this one isn't going to change your nucleus at all. After 32 days, 5. This one is exactly, basically, you see the pattern of what you need to do. Which reaction converts an atom from one element of an atom to another? Transmutation is going to change it. Okay? Which statement best describes what happens in a fission reaction? So, fission, it's going to split. So, it's going to split into a lighter nucleus. Nuclear fusion differs from nuclear fission because nuclear fusion reactions, so fusion is going to form heavier isotopes from lighter. Uranium-234 is used to make dental crowns appear brighter. The alpha decay of 234 produces what isotope? So, for this one, hold on, let me pull up my periodic table again. So it says through alpha decay. So uranium, it has a mass of 234 and a atomic number of 92. So this, you're going to put your arrow because it's showing a reaction is happening. Alpha decay is 4 of a mass, 2 of charge. Here's our particle, plus, remember, everything on this side needs to equal everything on that side. Okay, so what you're going to do is you're going to do 234 minus 4. It's going to give you 230. and then you're going to do 90 minus 2, and that's going to give you, 92 minus 2, that's going to give you 90, and this is going to make that element. It's going to produce that isotope. Flaws in welded metal parts of airplanes can be identified by placing the isotope iridium-192 on the side of the weld and photographic film on the other side to detect gamma rays that pass through. How does the gamma radiation affect the atomic number and mass of iridium? It doesn't. Remember, it has gamma equals no mass, no charge. So it's not going to affect your nucleus. What is the significance of the band of stability? Determines if element, actually not element, what is this? Nucleus. If nucleus is stable. Okay? So calculate the proton to the neutron to proton ratio of each, and then write a balanced equation for alpha decay of americium 234 or 241. I'm sorry. Okay, so 10. Ooh, where is? Hold on, my periodic table is playing games right now. Ooh, I just need one that works. Hold on a second, y'all. I need my textbook. Okay, so 10. 134. Oh my gosh. Oh, there we go. Okay. So 10 has 50 protons. So 50, you're going to subtract 134 minus 50 equals 84. So that is your proton to neutron ratio. Silver has 47 protons. So 107 minus 47 equals 60. Carbon 12 has 6 protons, 6 neutrons. Carbon 14 has 6 and 8. Okay, so then so for alpha decay of americium 241, so we're going to do 241. Hold on, let's find it in the periodic table. Okay, so americium is going to have 95 protons, and the symbol is AM. Okay, so we're going to put our arrow, it's going to go through alpha decay, so 4 to alpha. Ooh, it's a little crooked. Alpha, and then plus, you're going to subtract. So 241 minus 4 is going to equal 237. 95 minus 2 is going to equal 93. And the atomic symbol for that one is neptunium. Neptunium. Okay, so cesium 137 with beta 137. Cesium is going to have an atomic number of 55. And the letter or the symbol is CS. So beta decay is going to be 0 mass, but a -1 charge, and then the beta symbol. So with this one, remember, you're going to be subtracting it regardless. So let's do orange just so we can differentiate. So 137 minus 0 is going to equal 0. Or I'm sorry, 137. What am I doing? 137, and then 55, so you're subtracting a negative. So in reality, you're going to be adding. So 55 plus 1 is going to be 56. So you end up with barium, Ba. So that is the equation. Okay? Please let me know if you need anything. Ooh, wait. Please let me know if you need anything. I'm going to post a Zoom link for tomorrow morning. Yeah,